Before we get into the whole future-proofing thing, I'd like to start with a very brief overview of non-destructive testing. You may know a little bit about NDT, maybe you know about mag particle testing or fluorescent testing, penetrant testing. I'm going to give a very cursory overview just as a grounder, and then from there we'll move on. Okay, so this will move swiftly. These are the 7 most common non-destructing testing disciplines. There are several more, but these are the 7 most common. And what I would tell you about them is no one of these is better or superior to the others. They are all useful when applied in their areas of strength, but they also all come with limitations. So selecting among these is really the core of what we do at AMS. We help our clients identify which of these methods or which combination of these methods makes sense to apply for each challenge that they face. That's the core of what we do. We're going to walk through each of them briefly. I'll point out just a few characteristics. If you want a copy of the presentation, come see us in the exhibit area. You'll have all the slides. I'm not going to talk about all the bullets. There's going to be a whole bunch of material passed by. By design, I have to go fast, okay? So you can get a copy of it if you like. So the first and obviously most common inspection method is visual testing. We've all done this from the time we were about 2 years old. We're all non-destructive test technicians because we all do visual testing every day. It comes in a lot of different flavors, some simple, some a little more sophisticated. We might just put an eye on a part like the gentleman on the right. We might use a visual aid like you see on the left. We might use a vision system on the left here. We might do a remote exam like the guy on the right. In any case, it's visual inspection. It's the oldest and most common method. It's inexpensive to enact, but it comes with limitations. If we're doing it with humans, it comes with human limitations, and it has to be regarded as generally unreliable, okay? If you'd use a vision system, reliability is a function of the programming and the what is it you're trying to find. So we have to be aware of the limitations. Next up is penetrant testing. There are 2 primary methods. You may have heard about fluorescent penetrant on the left. There's also dye penetrant on the right. What makes penetrant testing work is capillary action. That's the key thing here. Capillary action draws the penetrant into the flaw, into the crack, and it's that same capillary action that will actually draw the penetrant back out of the crack to reveal an indication. So capillary action is the key that drives penetrant testing. In terms of important characteristics, well, penetrant testing is ideal for large, complex parts, complex surfaces, a gas turbine engine blade, a crankshaft in an automobile engine. That's a classic example of fluorescent penetrant. Really complicated surfaces. At arm's length away, I can get an indication that there's a flaw there. What about limitations? Well, you're only going to see surface breaking flaws. If it's a subsurface flaw, can't see it because the capillary action won't get the penetrant that deep into the part. It can't find that crack. It can't reveal that crack. So surface breaking only, okay? Next up, magnetic particle. So with mag particle, we have magnetic particles, dust if you will, that has dye embedded in it. We charge the part, we create a magnetic field, and those particles are drawn to areas of flux leakage, and because they have dye embedded in them, we now have a visual indication. Looks just like the photograph on the previous slide, okay? Usually under black light, we can see them. So another great technique for really large parts with complex surfaces. Again, at arm's length, under a black light, I can see those indications. But here again, we have a technique that's only suitable for surface breaking defects and only suitable where parts are magnetic. Can you do this on a plastic part? No, not magnetic. How about aluminum? No, okay? It's got to be magnetic. Next up, electromagnetic testing. You may have heard it called eddy current testing. Again, there are a number of other disciplines in non-destructive testing that I'm not talking about. These are the most common. So for electromagnetic, we're going to key on eddy current testing. So with eddy current, we put a coil next to the part, we induce a current in the part. That current sets off eddy currents. Those eddy currents create their own magnetic fields, and it's actually the magnetic field of the eddy currents that we measure. And they tell us about the possibility of a flaw being there, and they might also tell us about the material itself, okay? So what are some strengths with eddy current? It is fantastic for detecting surface breaking flaws, even very, very small ones that are difficult to see with the penetrant method or with the mag particle method. Sometimes those indications, while they're visible, are so small that even under black light, they're tough to pick up. They're not tough to pick up with eddy current. You can see it very clearly. We get a signal on a screen, and that tells us the part has an issue, okay? What are the drawbacks with eddy current? Well, A, it has to be something electromagnetic. B, it has to be surface breaking or very near to surface breaking. Steel parts pose an extra special challenge because it's very difficult to penetrate steel with magnetic fields. It's not very highly permeable, so you're very, very shallow in your depth of penetration in a steel part. Okay? X-ray. I think we all know about X-ray. Hopefully we don't have any artificial joints, but we know a little bit about X-ray. What I'll tell you about X-ray, gamma ray, all radiographic testing, it is a comparative technique. Look at the slides, and you'll see a scale on the slide next to the images, next to each of the images. And that scale is telling you how much volume you're seeing. So the shade of the scale indicates the volume. Radiography is a volumetric inspection technique. Okay, and I'm already jumping ahead of myself here. You know about X-ray. I'm not going to try and explain how it works. I think that we all understand it generically. Digital X-ray and CT scanning, these are huge advancements in terms of visualization and what we can see, fantastic tools. Now, generally speaking about X-ray, fantastic for looking at an entire system. I can inspect a piece part, I can inspect an entire engine assembly. That's awesome. Most other techniques, you can't inspect an assembly. You struggle to do it, right? This technique is great for that. It's great for finding volumetric flaws. The counterpoint to that is it's not so great at finding linear or planar flaws. Something that lacks volume is difficult to see with X-ray, okay? And we saw that on the scale, right? The other drawback to X-ray is it's relatively slow. It has a relatively slow cycle time, and it requires pretty expensive, sophisticated equipment. So those are some of the issues from a more practical standpoint. Next up, ultrasonic inspection. The two images showed two different immersion ultrasonic inspection systems. With all ultrasonic testing, what we're doing is putting sound into the part, and we're measuring the reflected sound. Okay, so if you look at the two little images, the one on the left, you can see in gray color is a part. So we're putting sound into the part, it's reflecting off the back wall of the part. I get a signal when it enters the surface of the part, I get another signal when it hits the back wall. On the right-hand side, I get a signal in between those two. Wait a minute, there's not supposed to be anything there. That might be a flaw. We can tell from the time at which we see the signal, and we can tell from the amplitude that something may be there. So we're measuring reflected sound to identify the possibility of a flaw. What's great about ultrasonic inspection is, unlike some of the surface breaking techniques, ultrasound will penetrate through the entire part. Doesn't matter if the thickness is 1 millimeter or 10 millimeters or 100 millimeters or larger, we can get sound through the entire part. So we can find subsurface flaws. So in parts like pressure vessels, for example, you want to find any structural risk in that pressure vessel, and that structural risk is more likely to live in the middle of the part than it is on the surface of the part in some cases. So we definitely want to be able to get to the middle of the parts. That is what ultrasound does exceptionally well. Superior depth of penetration versus virtually all the other methods. What are the drawbacks to ultrasound? The most obvious and significant drawback is that with ultrasound, we need to have a couplant. Sound doesn't travel well through air. It travels much better through a couplant, water as an example. So the reason we can hear whales from 7 miles away is the ocean is acting as a couplant, and that sound is traveling very effectively through the water, much more effectively than it would through the air. Okay? We have to have couplant. So if you manufacture castings and they're iron and porous, you maybe don't want to put them in an immersion UT tank because you don't want to deal with that water now entering the porosity of the part and posing a corrosion risk, right? So we have to think about some of the practical limitations. So need for a couplant is the biggest issue with ultrasound. This is another technique called acoustic resonance. You may hear it called a tap test. We strike a part, we cause the part to vibrate or resonate. We listen to that. We do some arithmetic to plot the microphone signal in the frequency domain, and we get a waveform. And if you look at the picture second from the right, there's a waveform. And again, on the right-hand side, you see the waveform. We can look at the waveform of a part and identify, is that part ringing the way a normal part rings, or is it not ringing the way a normal part rings? And that's what acoustic resonance inspection does. Strike the part, evaluate the waveform. Is the part normal or not normal? If it's not normal, you set it aside. If it's normal, you pass it on into production, okay? Acoustic resonance is great at identifying structural defects of all types. You can find material, what I call material funkiness. So if there's some issue with the material contamination or just it's out of spec, you can oftentimes find that. You can find structural flaws, et cetera. The limitations of acoustic resonance testing are that it is a qualitative test. All I can tell you is that that rejected part is not normal. I can't tell you why. I can't tell you what kind of flaw, what size flaw, where the flaw is. I can't tell you anything. All I can say is it's not normal. If we want to know more about it, we have to examine it with other methods.